Hello, do we have anyone online? Oh, there we go. Sounds like we still have a bit of a delay here. Usually I would. Do we have anyone online? Sorry, turn that off. Okay. Okay. Okay, welcome to the bleeding edge here. This is not quite the setup I would usually have, but my mic isn't working today, so this is the backup plan. Vote for your favorite moments. Okay, welcome everyone. Let's start thinking about biostatistics now instead of the technology. I wonder if I can change the size of this here. Perhaps not. Okay. Okay, so we're going to have another class of descriptive statistics today. Yesterday was just about some of the basic variable types and showing some plots of those. I'm going to show you some more graphing stuff today, and also numeric summaries. So all of this is under what we call descriptive statistics. It's not about inference or testing hypotheses. Instead, it's just about describing your data and taking what was maybe a huge spreadsheet of numbers and boiling it down so you can understand it a little bit better. So I will go quickly over the stuff that we did last class and get into these few other things. These are some plot types just for single variables, no bivariate analysis yet. Oh boy, this is quite the delay here. I switched to the second slide some time ago. Live. This is kind of a broad definition of live here. Yeah. This is not going to work if that's what it's going to be like. Let's see if we have a VGA cable. Yes. Okay, maybe I can do that. Oh, it did change slides finally. Hi, Tony. So let's see what happens if I go to slide 3 now. Is it still going? Yeah, it's still taking its time. Okay, there we go. Oh, this is very interesting though. Sorry. We can go. Okay, Tony can see and hear us. Okay, this is actually very clever because now I can show this to you in full screen. Welcome. And if any of you notice someone asking a question here, would you let me know? Okay, I think we're finally working now. So welcome everyone, and apologies I wasn't able to get the notes to you today. The printing office closed early, and I didn't realize that was happening. So I have printed note or handouts for you, and they're all sitting locked up on the 3rd floor. Next time I'll have them for you. Okay, so I introduced the idea to you of a population and a sample, which is something that's going to be a continuing theme throughout the course. The population being the collection of everyone of interest in a study, and the sample being just one selected subset of that. And we're going to talk a lot about sampling population distributions versus sampling distributions later. Sampling distributions being what you get when you repeatedly sample from a population. But for now, it's enough just to know the difference between a population and a sample. The record or observation, that is one data point, if you will, from the sample. Descriptive statistics, what we're talking about so far, just describing your data, and inferential statistics being the hypothesis testing and drawing inference about the population from the sample. So we covered several different types of variables last time, random variables, and variables that we observe. The nominal type, which were nominally really a number. They're actually things that we might code with numbers for computational convenience, but they're things like treatment group, sex, etc. And ordinal being also not fully a number, but just having an order. So there, again, might be coded as numbers for convenience, but you could just as easily write out first, second, third, instead of using 1, 2, 3, and the quantitative variables, which are what we can do math on and add, subtract, etc. For summarizing the nominal and ordinal data types, we use tables, contingency tables or frequency tables, and bar plots. And all these do is show you the number of counts in each category. Can also do this with the pie chart. A lot of people don't really like pie charts. I think they're great if you have an actual pie. And other than that, they're you know, they can look nice, they can be funny and things, but they're not actually as informative as a bar plot, because you can't, it's hard to read what the proportions actually are compared to a bar chart like this, where you can actually directly read what those proportions are. So frequencies are just the counts. Proportions are the counts divided by the total number of records or observations, and percentages multiplied by 100. Apologies if this is all pretty basic stuff. I want to have kind of a gentle introduction to the course. Believe me, it's going to accelerate as we go along. I'd been told in the past that students got a bit overwhelmed right up front by the course, and that I should try and ramp it up as we go. So that's what I'm going to try to do. For plotting quantitative variables, so we've got the bar plot for the categorical nominal variables. There are a bunch of different ways that we can plot quantitative variables. The dot plot, this is the one-dimensional equivalent of the scatter plot. This is kind of the most information, where you show every single data point. Histogram is somewhat more summarized, still a lot of information depending on what size of bins you choose for the histogram. And then the box plot is more summarized yet, just showing a single box for that one set of observations. We'll talk a bit now about how to use and interpret these. Here is an example of a dot plot. So this is showing some data points like a histogram, but actually showing every individual data point. This is kind of an extension of the strip chart that I showed last time, but for when there are actual exactly tied variables like this, you can actually see them all because they stack up on top of each other. The histogram, again, is just where you divide these into bins and show the counts in each of those bins, and they're ordered. So you're taking a quantitative variable and turning it into an ordinal variable, which you can then make a bar chart for. That's called a histogram. You can choose the amount of information in a histogram by the number of bins, and whichever software you use, it will have an option for choosing this. It's a good idea when you're exploring your data, potentially to try a couple of different sizes, because it can look, your visual summary can look very different depending on what size of bins you choose here. The main things that we are looking for in a histogram, and in general descriptions of our data, are the center, the spread, the range over which it occurs, and the shape of it. So it's like the central tendency, how spread out are your observations, and what kind of a shape do they have. So shape, skew is one aspect of shape, and this is showing a density plot here, the kind of extreme end of a histogram. This is a symmetric normal type distribution. So the left and right side are mirror images. This is a left skewed distribution. So this is something like age at death, where there tend to be more common for death to occur around one set of ages. So I have with younger ages, death occurring less commonly. And a right skew, an example of where this happens is incomes. You have a lot of people with a middle income and then a very long tail of high incomes. This is also what apparently rents in New York look like, although I don't know, maybe it's more like this. It's what it feels like when I was looking for an apartment. So just a bit more description of skew. It's where you have a tendency for individual observations to occur very far away from where the majority of them are occurring, such as with lifespan and income. Another aspect of shape is modality. So on the left here is a unimodal distribution. On the right is a bimodal distribution. Mode being a most common value, and the point here being that if you said what is the most common value, there are really two different distributions here. And there's obviously some difference between this set of observations and this set of observations, and they have two different modes. Outliers are individual values that occur a long ways away from most of the values. There are various definitions of outliers. One common definition is the median plus, I think it is 2.5 times the interquartile range, but it's kind of arbitrary. An outlier is just something that looks unusual. Such as this data point here. Might be caused by errors in measurement or recording, or it might actually be some might be something true about this particular individual, and it may actually be an aspect of your distribution. Certain distributions tend to have outliers. Yes, question. Oh, there's a question. Thank you. Yes. Let's see. Question is, why can't I see the current slides? Which I believe, unfortunately, is something out of my control. Where's the... Yeah. Oh, wait a minute. Am I? Oh, I'm showing them here. There seems to be, hi Hootie, there seems to be a lag here between the slide that I am showing and what I'm saying. I would recommend opening up the PowerPoint from Blackboard and following along, and I'll tell you when I'm changing slides. I'm going to see here, though, if they're, because it's showing like this here, too. Oh, now it's there. Okay, let me see. Oh, okay, maybe. Okay. It's not as far behind now. Okay. Okay. Well, it'd be nice if at least the video and the audio would lag by the same amount, but we'll see. Yeah. In the meantime, we are on the outliers slide right now, page 16. And I just finished discussing that outliers are just like they sound, something that looks far away from the rest of the distribution. For a single quantitative distribution, you introduce the box plot. The key components of the box plot here. In the box, there is the median, or the second quartile, the 50th percentile, the 25th and 75th. The whiskers extend out to the median plus 1.5 times the interquartile range, and then outliers are anything outside of that. And note that the whiskers aren't necessarily always the same length because it will only extend out to the furthest data point. So if you have nothing that is beyond 1.5 times the interquartile range, then you'll have a shorter whisker on that side. And this just shows it up compared to a continuous distribution here to give you an idea of what those first, second, and third quartiles look like here. This difference between the third and the first quartile is the interquartile range, which is an alternative, one of the measures of spread of a distribution, of the center of the distribution. So you can do a box plot like that for one distribution, but they're especially useful for comparing two distributions and quickly seeing how those centers of the distributions overlap, as well as where the outliers are. It's a very compact. If you wanted to show histograms for several groups, it would become very unwieldy, but the box plot is compact enough that you can quite easily show several distributions and immediately compare them as to where the center and the quartiles of the distribution are. By the way, in R, there's an option to add a notch to these boxes, which is a little sort of bite taken out of them, and where those notches don't overlap, you can probably reject the null hypothesis of those samples being from the same distribution. Kind of outside the scope of what you need to do, but it's interesting to know. Okay, so here are the main numerical summaries that we use to describe distributions. Mean, median, and mode for the central tendency, the quartiles and percentiles to describe different parts of the distribution. The range tells you the extremes, and the standard deviation is another measure of spread that turns out to be very useful. You all know what the mean is. It's just the sum of all of the observations divided by the number of observations. Is everyone familiar with the capital sigma notation for summations? Okay. So here are some examples, and I think I gave some code last time for generating these samples in R. 4 different distributions: the normal distribution, which we use all the time here. Log normal is a distribution where if you take the logarithm of it, you get a normal distribution. The exponential distribution, the probabilities are exponentially decreasing towards 0, and a uniform distribution where you have an upper and a lower bound and equal probability of having an observation anywhere in between there. So looking at these on a box plot, sorry everyone, we're on slide 21 now. I have to remember to update this. The normal distribution and the uniform distribution, you'll notice that the mean and the median are approximately equal. That's a sign that there is no skew and there are not really outliers in these distributions. When you see a difference between the mean and the median, such as the log normal and the exponential distribution, that is happening because of the skew in these distributions. And that's often used as a measure of skewness or outliers, is the difference between the mean and the median. So important thing here is that the mean is strongly influenced by outlying values and by skew. So the median is just the 50th percentile, where half your observations are above, half are below. It's the middle observation, regardless of how big your end observations are. So this is what we mean by median is resistant. You can do anything you want to the outer values and it doesn't change. The canonical example being the 7 dwarves, and even if one of them grows up to be a basketball player, it doesn't change the median. All right. Mode, I don't use mode too often, but it is, I guess, occasionally useful as a description of a categorical data set. It's just the most frequent category. So it's only defined for categorical variables or for if you have categorized a quantitative variable, such as in a histogram. Of course, your mode can change. If it's a histogram and you change the size of your bins, your mode can change. So it's not a well-defined variable for quantitative variables. So here's just the demonstration of what I meant about how the difference between median and mode can describe skewness. So with the right skew here, the mode, if we bin this, is here at the highest point, the median over to the right some, and the mean being influenced more by the outlying values is further to the right. And the same thing in the other direction for the left skew. So even if you never plot these, if you just, there is, for example, the so-called 5-number summary that is the mean, median, minimum, maximum, and standard deviation. Just from that, you can get an idea of whether there's skew in your data set if you start getting used to looking at those numeric summaries. So the percentiles, this is gain equivalent to the quantiles. It's just multiplied by 100, and it's the percentage of the observations that fall at or below the given value. Note that this usually refers to the distribution, not necessarily to the sample. So in a lot of software, when you calculate the quantile or the percentile, it doesn't do it just by counting the number of data points that are below there. It actually will estimate a distribution from it and calculate the quantile from that. Page 27, percentiles. Boy, that is really not moving at all. So strange. Okay. The quartiles, these are just the 25th, 50th, and 75 percentiles. There's nothing special about them, but we use them a lot to describe a distribution. Just because they're on the box plot, they're kind of standard positions to describe when you use the summary function in R and sort of the crosstabs method in SPSS with quantitative variable. It will tell you what the quartiles are: the 25th, the median, and the 75th. The range is the least robust measure of spread, so it is exquisitely sensitive to outliers. It's just the difference between the maximum and the minimum value. So from the same distribution, to give you an idea of what I mean here, if we estimate the standard deviation, the interquartile range, the mean, the median, the more observations you make, the more stable they will become. So they will just converge on the population value. The range will never converge. The more observations you take, the larger your range will tend to become. So it's not a stable measure of spread. So it might be useful to know, just to know what your extremes are, but it's not really a good description of, it's not a good way to get an idea about the population from your sample. So yeah, just the maximum minus the minimum value. So variance and standard deviation, these are the measures that we actually use in inference. The t-test, analysis of variance, these main things that we're going to do in principles of biostat are based on an analysis of the variance, including the t-test. All it is an average squared deviance. So x bar here for a variable x bar is the mean, xi are the individual observations. We just subtract the mean from every one of them, square it, sum these up, and now for a population, if these were all of the observations, we would divide by n. For a sample, we divide by n minus 1. And that's just kind of a quirk to make this an unbiased estimate from the population. Anyone have an idea of what the bias would be if you estimated the variance from a sample and divided by n instead of n minus 1? Mm-hmm. Right. Do you have any idea of why? There's some kind of a qualitative explanation. No. It's because you're estimating the mean from the sample. And you put the mean in the place that minimizes the variance. So if somehow you knew the population mean, and then you were calculating the variances using the population mean, you wouldn't need to divide by n minus 1. But for example, you take two measurements, you're going to put the mean right in between them. That is the spot that minimizes the variance, even though that is not where the true mean is. So just to give you an idea of what this looks like, I plotted these are the same samples that I showed before in the box plot, but showing you each individual observation. And this is a sample drawn from these same 4 distributions, normal, log, normal, exponential, and uniform, with the horizontal line here is showing the true population mean. Of course, if I were estimating this from the sample, it would be a little bit off from 0. And these red lines are showing the x minus x bar. The squares, so comparing, so that was page 31, now we're on page 32. When you square this, you really make those outliers stand out further. So when we're just looking at x minus x bar on the log normal, there's a fairly substantial difference, say between 1 and 10, between the most of them and the large ones. It becomes much, much bigger on the squared scale here. So now it's like a couple of order of magnitudes larger now that it's squared. So that's why, yes, question? Yes, it's the same data set. Yeah, so I took the same, I drew a sample of 40 observations from each of these distributions. And then I just plotted for each one of those data points in order from 1 to 40, the difference from the mean and the squared difference from the mean, just to show you what happens when you square it. So you notice they're all positive here, whereas there are negative ones before, and you notice how much more extreme the difference from the small ones to the large one becomes on the squared scale. Yes, question? It means that if you were to take these data points and take a log of all of them, then they would look normally distributed. That it's just a different sampling distribution. It's the values are all positive because you can only take the log of positive values, and it just has a very long tail to it, because from the normal distribution, you square it, the things that were outliers become super outliers after you take the exponential. These are transformations that we use sometimes to try and get a normally distributed variable, which has desirable properties. Log transforming a variable is a pretty common transformation, which is why I mentioned the log normal distribution. We'll get into it with the hypothesis testing, but for the t-test, for the analysis of variance, for regression, one of the assumptions of all of these is that our response variable is normally distributed conditionally on the predictor. The way that coefficients are calculated and the p-values isn't valid for non-normally distributed values. So you can imagine when you calculate a p-value, you're basically calculating the probability of getting an extreme, a sample that's as extreme as yours or more extreme. That's based on an assumption of how what your distribution is. And if your true distribution has is different, like say it were log normal and it has more outliers, then actually your probability of getting something extreme might be higher, and your p-value will be invalid. That's kind of roughly why we would want to do transformations. Everything is easier if you have normally distributed variables. So we tend to try hard to make them normal if we can. So here's some key things to know about the standard deviation. It's on the same measurement scale as the observed variable. So if your observed variable is age in years, standard deviation is age in years. It's a measure of the spread of the data. If it's normally distributed, we'll have something called the empirical rule to describe the spread. I didn't actually put empirical rule in here today. It might be covered in lab, or otherwise I'm going to cover it later. When all your observations are the same, there's zero standard deviation, and as your data becomes more spread out, your standard deviation is larger. So you can imagine a uniform distribution across the same range will have a larger standard deviation than a normal distribution. And a bimodal distribution at the extremes will have the largest standard deviation that you can have for a given range. And as I mentioned, it's not resistance, so it's sensitive both to skew and to outliers. Here are those same favorite four distributions again, just to show you. So here's the mean in the bold-faced red, and then plus or minus 1 standard deviation and plus or minus 2 standard deviations. So for the normal distribution, plus or minus a standard deviation is kind of close to the interquartile range. Also for the uniform distribution. Yes, question?
I'm familiar with the normal. You explained the log normal. I guess essential.
Yeah. The uniform, you have a given maximum and minimum, so the only things that you need to specify are your range, your minimum and maximum, and then your probability of an observation is equal anywhere within the range. So, uniformly distributed ages between 0 and 100, which mean you have the same number of people across that entire age range, the same expected number of people at every age. Any more questions? Okay. They're still on outliers. No. Okay. So, and again, you notice with the log normal distribution, the standard deviation is being drawn way out by these outliers. It's much larger than in the other distributions. Can't even see it on the negative side here. So these are all our measures of spread, the interquartile range that I measured. This is one that I actually use all the time. It's a very nice resistant measure, very useful, about the center of the distribution. Mean absolute deviation, or MAD. You will see this used sometimes. It's just if you calculate your median and take the difference from every data point to the median, and then take the median of that. It's another very resistant measure. And and the range, which is not robust. All right, so here's our vocabulary summary. A few plots: the mean, median, mode, percentiles, quartiles, the interquartile range, standard deviation, MAD. Capital sigma notation that I'll be using to describe sums, unimodal, bimodal, and skew and outliers. I think we have a fairly kind of burned through lecture today. So we'll get out a few minutes early. I think can I get a quick show of hands here? How is put up? I don't know. Just go like this if you feel like the course can go faster. This if you think it's should slow down, or just like this if you think it's about right. Okay, I see a lot of about rights mostly. Okay, it is going to speed up a bit, but I try to keep a fairly even keel through here, and I really tend to spend a fair bit of time. My own lecturing theory is spend a lot of time hammering the important points in class, and then the details you get familiar with during assignments and during labs and things like that. So I try not to have too fast a paced lecture, and make a chance to repeat some things and for everyone to ask questions. Are there any more questions about any of this stuff? Okay. Let's reconvene at 6 o'clock down in the lab, and I will be down there as well. This time I'm going to try and figure this out. Yeah. No, it doesn't describe modality. No, it's really just a measure of variability, and it doesn't tell you anything about modality. It doesn't tell you about the distribution either. I mean, it doesn't tell you about the shape of the distribution. It's affected by the shape of the distribution and the modality. And it's not a very good measure of spread unless you have a kind of symmetric distribution. So, yeah, no problem. Hi.
Quick question. These live questions, can they be viewed later on YouTube?
Yes, for what it's worth. I think it turned out not very well today, but I never had such a problem before.